on spectral partitioning metrics.
All right. Thanks for the introduction. Thanks for the invitation. This bunch of co-authors are Asaf Naor, Sasha Nikolov, Ilya Rosenstein, who is in the audience, and Eric Meingarten, who is also in the audience right here. This is this title is Spectral Partitioning for Metrics. It's also about nearest neighbor search. It's a workshop on that. So has to relate, and I guess it feels weird to define nearest neighbor search at a workshop whose title includes that. But I'll do it anyways. Maybe there is online audience, and also to set up notation. So I'll talk, about approximate nearest neighbor search, where it's a data structure question where we have endpoints in a general metric space X, and I'll return to the question of what is this metric space X in a second, and we'll denote this by P, a bunch of points, and we need to pre-process so that we can answer queries where we have two parameters, the approximation, which we'll denote by C, bigger than 1, and distance threshold, R, bigger than 0. Think about this as we want points which are within distance. We want to report points within distance R. So, okay, let me just define this. The query means that we get a new point Q, this red point, so that we can report any point within distance R, that would be the exact near neighbor. The approximate version says that assuming that there is a point within distance R from our query, we want to report anything which is within distance CR. Okay, so if there is no point which is within distance R from Q, then the data structure can do anything it wants. But if there exists a point within distance R, then it should report something which is from a ball a little bit larger by a factor of C. Okay, so this is kind of the standard definition of the approximate near neighbor for a particular distance threshold R. So, it's kind of the correspondence to practice is that we'll report points which are at least this similar, right, where this is concrete threshold. And it has tight connection to the nearest neighbor, where we want to report the approximate, the point which is within, whose distance is within factor C of the point which is the closest to the query point Q. Okay, but here I'll focus on this near neighbor where we have this threshold R, just because it's usually easier to design algorithms, or at least the algorithms of our type, for this problem. Okay, and the main parameters here, or kind of the usual trade-off, is to obtain approximation versus space versus query time. Usually kind of the biggest trade-off, or the usual the biggest tension is between approximation versus space and query time. At least this is what will be the focus of today. Okay, so this is standard definition, and just quickly to go through kind of the main points, or the main kind of setup of this problem. So I guess frequently asked questions. Why approximate? Why are we focusing on approximate nearest neighbor search? Well, here we're focusing on the high-dimensional case. In high-dimensional case, the exact nearest neighbor search is usually hard. Depending on the exact model of what exactly it means hard, one can prove, for example, based either some data structure lower bounds, or say based on Ceph, so on strong exponential time hypothesis. Under additional assumptions, you can pretty much exclude non-trivial algorithms for high-dimensional situation. Okay. So what does it mean? So here I'm saying high-dimensional problem. What does high-dimensional mean? We'll usually think of dimension as being at least logarithmic in the number of points. So it's at least log n with very a little bit more than log n, let's say. Okay, so but what is dimension, right? So at the moment I said metric space. What is the dimension of metric space? Well, so how do we define dimension? So first of all, oftentimes, and for the rest of the talk pretty much, I'll talk about metrics which are defined on real space, d-dimensional real space. But there are alternative notions of dimension, for example, doubling dimension of a metric space and so forth. Okay, but again, here we'll talk about the metric spaces on d-dimensional real spaces, and we'll think of dimension as being, again, a little bit more than logarithmic in n. We'll also think of dimension as being smaller than polynomial in n in the data set, just because when it's bigger, then kind of other types of algorithms kick in. Okay, and most importantly, what we'd like to obtain is a dependence on dimension which is polynomial. Okay, as opposed to exponential in dimension algorithms. So this is, this is the setup and this is the goal. Okay, so now, let me kind of, get a little bit more specific now. So which metrics to use? Okay, so this is, a little bit more specific to this talk. So which metric to use? And this is kind of, the main question that, we are looking at kind of in this line of work. And in general, kind of, from kind of application perspective, you want to use nearest neighbor search under a metric which captures the semantic similarity well, right? So one of the main applications for nearest neighbor search is similarity search. Given you have a data set of objects, you are given a new object, you want to find similar ones, perhaps for labeling classification. So you want, when you're comparing objects, images or texts, right? You want to define on these objects certain kind of distance so that it captures the semantic similarity, what we mean for objects to be similar, to capture it well. At the same time, of course, you can create pretty crazy distances, but it's very easy to create ones which will be, very hard to design algorithms for, or at least non-trivial algorithms. And there is usual tension kind of, but you want to define semantic similarity, define distance function that has, captures semantic similarity, similarity, and must be algorithmically tractable. In practice, oftentimes, what you'll do is that you'll define a simple distance function, for which there is algorithms, and this will be a pretty important kind of consideration. So, here we kind of want to step back from that general approach and say, okay, can we design nearest neighbor search for more general metrics? Can we build kind of more of a theory of nearest neighbor search for more general classes of metrics? Okay. I should mention, some examples of metric spaces, and this is not quite in order of hardness, but roughly, of course, kind of some of the easiest high-dimensional spaces are Hamming space or Euclidean space, but there are kind of more specialized distances, for example, Earth-mover distance, which is kind of more specific to image vision. But you can also imagine other distances, for example, spectral norm for distance between matrices.
What about edit distance, or is not one you?
Edit distance is one of them, but it would go over in second line. So yes, I'll actually get to that distance at at the last slide actually. But yes, edit distance as well. Though all examples here are norms. Edit distance is not a norm. And I'll get to norm versus no norms later in the talk. Okay, so the general goal of this all this rambling of mine is pretty much to get to this goal. That what is the goal of our project is to try to understand or classify the complexity of nearest neighbor search as a function of a metric. Okay, so from theoretical perspective, you can think about this question as, what property of a metric space make it hard or easy for nearest neighbor search? Okay, and from practical perspective, the reasoning or the motivation comes that if we manage to design nearest neighbor search that is, somehow works for a generic metric, maybe somehow the complexity of it depends on the property of the metric, but the algorithm is kind of more generic that applies to many metrics at the same time, then it must be a certain kind of universal algorithm for nearest neighbor search that somehow adapts to the metric. And this is important in practice because oftentimes you'll design a particular metric for comparing your objects, and it's often to tinker with it. We'll modify it a little bit here, a little bit there, and you don't want to say that suddenly the geometry of a space changes a little bit and you have to redesign the algorithm from scratch. It would be nice to have an algorithm that somehow, is resilient to these changes. Okay, and, hopefully answering or approaching this goal will, give such a universal algorithm. Okay, and let me give, what I would call not quite solution. I mean, it's solution in other situations, but something that doesn't quite give a solution for this particular goal. This is designing approximate nearest neighbor searches for any metric with small doubling dimension. Okay, so this is line of work that applies for any metric. So it says that it's nearest neighbor search where the only information I get from a metric is that I can ask black box what is the distance between these 2 points. Okay, given IDs of 2 points, there is a black box that says what is the distance. So assuming that this metric space has low doubling dimension, there are algorithms that started with work of Ken Clarkson, but also appeared in other papers, were improved in other papers. We obtained algorithms that work with this black box. So in the sense we work for any metric. Okay, the caveat is, and why it's not quite a solution for us, is that the algorithms will have exponential dependence on this doubling dimension. Okay, so while we work for any metric, the dependence on dimension, doubling dimension here because it's a generic metric, will be exponential. What we want polynomial dependence on dimension. Okay, so you think about this as a kind of generic algorithm for nearest neighbor search, but it is for low dimensional spaces. We want to do this for high dimensional spaces.
So you want polynomial dependence on dimension?
We want
the log n type thing?
Yeah, I mean, we want polynomial dependence on dimension. We'll see what is dependence on n. Whatever is the best dependence on n we can get, the better, right? And in general, it will be a trade-off between approximation and, I guess, this dependence on n in space and query time. Okay, I'll give an example pretty much on the next slide. So, let's see what, the type of algorithms we can get for high dimensional case in general. And the simplest case, high dimensional case, the simplest one is basically L1 and L2 metrics, norms. This is something that has been studied a lot. And basically most of the nearest neighbor search data structures that have been designed so far in the literature are for Hamming and Euclidean spaces. And it started with locality sensitive hashing, which was the first algorithms that obtained polynomial dependence on dimension. I guess later work kind of gave the best known algorithms for L1 and L2 case are based on what is called now data dependent hashing. The type of bounds that you get is that the space will be n to 1 plus epsilon, query time is n to epsilon. So small polynomial loss in space and small polynomial in query time. And the approximation is something that depends on epsilon. So for Euclidean space, the best dependence is pretty much 1 over root epsilon. Okay, right. So in a sense, if we want to do this for general spaces, for general high-dimensional spaces, we don't really hope to do much better than this. But can we do this for general spaces? For general high-dimensional spaces, right? So this is the question. Okay, so general norms. Sorry, before that, so let's focus. Okay, talking about general metrics is hard. So let's focus a little bit more, narrow down a little bit more. Let's talk about norms. Okay, so what can we do for norms? So let's say we have d-dimensional real space and we consider all possible norms. Okay, which is subclass of metrics. What can we do there? So there we can do the following, a naive application of John's ellipsoid theorem, which says that any d-dimensional space is within factor of root dimension from d-dimensional Euclidean space. Okay, so pictorially, maybe kind of in convex geometry, you have seen the statement more like in this way, that any symmetric convex body K, there exists an ellipsoid E. So let's say this rectangle is our convex body K. There is an ellipsoid which is inside this convex body, and root descaling of this ellipsoid captures this convex body. Okay. So this is the theorem, and we can use this theorem to get some algorithm for any norm. So in particular, using this theorem directly, by the way, this is tight bound with ρD, even for spaces like L1 or L infinity. So and I call this kind of baseline approximate nearest neighbor search for norms, which proceeds very embedding, in particular with Jones ellipsoid. So what it immediately implies is the following, right? And this theorem is implied by taking a norm, applying the embedding from the previous slide, and then using a standard algorithm for nearest neighbor search in Euclidean space. Okay, so what we obtain is space will be again n to 1 plus epsilon, query time will be n to epsilon. The approximation will be now root d by epsilon. Okay, where root epsilon is the trade-off versus space and query time that we get for Euclidean space, and root d we get from mapping the Euclidean space, mapping the general norm into Euclidean space. Okay? So,
just one quick question. When you say d-dimensional norm space, what is the dimension of the norm space? What is the d?
It's defined on RD. Sorry, is there? Right, so this is our metric. It's d-dimensional real space with some norm.
So d is not induced by the norm. It's just the little d was not induced by the
It's
norm.
d-dimensional norm. Yeah. Sorry.
I'm saying the little d was not induced by the norm itself. It's just the little d of the RD.
Yes. Yes. Precisely. Okay. So this is okay. I mean, this is kind of what you can get using kind of standard or known theorems, and this leads me to our results. So this is the baseline algorithm for approximate nearest neighbor search that I just mentioned on the previous slide. I'm fixing epsilon to be a constant, just to simplify formulas here. So our paper, and this is what I'll mostly focus in this talk, shows that for any general norm, so any norm defined on a d-dimensional real space, we can get an approximate nearest neighbor search. We'll have the same space and query time, n to 1 plus epsilon space, n to epsilon query time, and which achieves approximation order log d, so an exponential improvement from this result. One caveat is that we don't quite get a data structure. We get what is called a cell probe, a data structure in the cell probe model. As in, the query time, this n to power epsilon query time, is not the total time that it takes to run the query time. It's actually more, but the number of probes into the data structure is n to power epsilon. Okay, so put differently, what it means is that we take the n-point data set, we preprocess it, we construct something which we write out in memory, which takes n to 1 plus epsilon space, and then at the query time we get a query point, and what we count only is how many times I look up this memory. I might do much more computation, but this is how many memory probes I'll do. Okay, and obviously this is not it's not real data structure. So in kind of our next work, and this is what Ilya will talk in the next talk, we can improve. We can get a real data structure where n to power epsilon is the actual query time of the data structure. The approximation goes to 2 to root log d. Okay, so somewhere between polylogarithmic and subpolynomial. Okay, and so this is the results for general norm. But it is a general technique that can be applied to many norms, and for many norms one can get better bounds. And for example, for LP spaces, where think of P as being bigger than 2, let's say, as well as for Schatten norms. So these are norms or matrices. One can obtain approximation which is order P. I should say for LP, this improves upon efficient nearest neighbor search, approximate nearest neighbor search algorithms that got exponential in P approximation before. And in particular, for spectral norm, this is basically Schatten where p is equal to infinity, one can get approximation which is order log d. Okay, and this, what I'm mentioning is that these are actual data structures. Okay, so it's not just cell probe. Other questions so far about the results? Okay, so for the rest of the talk, what I'll do is I'll talk about this general principle or general approach to designing nearest neighbor search that gets us these cell probe results, and it depends on a property of a metric that I'll define next, and then I'll show how this property of a metric gives rise to approximate nearest neighbor search, with specific approximation. Questions?
So the result with the Schatten norm is independent of D, so you can have arbitrary dimension.
Here, these results, yes. Yeah. This result is basically says that, well, Schatten infinity is pretty much the same as Schatten log D up to constant factor, therefore you get order log D. I mean, this is not really separate result from this one, it just follows.
And in the cell probe model, do you have any lower bound that shows that a dependence on D, like logarithmic, is necessary as well?
Oh, but this approximation order log D is necessary? We don't really have a lower bound for general norm pivot, no. We have just our particular approach to designing, yes, log D is optimal. But for data structures, no. I mean, in particular for L infinity, the approximation that a result of Piotr Indyk from 98 obtains is log D. We do not know whether for general norms we can get log D or not. But our particular approach gets log D only.
Actually, L infinity is the third example itself for our approach.
Yes, yeah, so as in our approach, L infinity already, we cannot beat log D approximation, even though in principle there is another algorithm that gets log D. Any more questions? Okay, so if not, let me talk about the new approach, right? And this is where the actual title of the talk comes, the spectral partitioning. It is, what is our new approach? Well, I'll define a new notion. We call it cutting modulus. It's a well-defined quantity for every metric, not just norm. We show that it governs the complexity of approximate nearest neighbor search. So all those results follow from obtaining bounds on this cutting modulus. And as a point, this notion goes beyond or obtains better results than you can obtain through metric embeddings, let's say into L2 Euclidean space or Hamming space, which were the usual approaches to obtaining algorithms beyond L1 or L2. Kind of another component, and this is pretty much connected to this point, how it governs the approximate nearest neighbor search, is that using this notion we're showing a new partitioning for metric spaces, which is based on this notion of cutting modulus. I should mention, especially for experts in the audience, this partitioning is not ball carving, or at least we don't know to show that ball carving actually works here. It might just as well, but it's not ball carving, which is a very classic way to do partitioning and obtains, for example, optimal algorithms for Euclidean space and so forth. Okay, so I'll define this cutting modulus, and if there is anything to get from this talk, this is probably the most important notion to get from the talk. And so let's do it. Okay, so again, it is defined for a metric space. We denote it by this Greek letter called Xi. It's has three connected components. It's I think we ran out of all the other Greek letters by the time. So this number, this Xi, is it depends on the metric and on epsilon, which is some parameter. So it is the following, the smallest number, such that the following holds. For any graph, so consider any graph, but we embed into our metric space M, such that all the edges have length at most r in this metric. Okay, So pictorially, I mean, it's not quite equivalent, but you can also think the following. I have my metric space. I put a bunch of points in this metric space. This will be my vertices of the graph. I connect the vertices if they are at distance at most r. Okay, I should say that this is such that for any r, the following holds. Okay, so r is this threshold that we care at the moment. Okay, so it pretty much saying, okay, consider a bunch of points in the metric space, build the r near neighbor in these for these points. Okay, so all these edges are between points which are distance at most r. Okay, so for any such graph that to draw, one of the following two must hold. Either there exists a ball of radius which is our parameter r times this parameter, the cutting modulus, in particular xc, that captures, let's say, a constant fraction of the points, let's say half of the points, okay, of the graph, or
what is the number you're trying to minimize? You said smallest number.
The smallest xc, such that the following holds.
Okay.
So, and n is the number of vertices of this graph?
Of the graph, yeah. Okay, or if this doesn't hold, then the graph must have an epsilon sparse cut. Okay, so for example, it is something like this. There exists a partition of the graph such that the conductance is at most epsilon.
So it's like saying if you try to embed an expander, all the points have to be close together.
Precisely.
To get
Precisely.
a fleet, basically, or something.
Right,
Like that.
right. So in a sense, exactly. So having C be very small means that you cannot really embed the expander into your graph. That's a very good intuition, yes, precisely. Right, this means that if C is very small, then this means that if you have like a very large expander, then the distances must collapse. Yeah, because it doesn't have epsilon sparse cuts. This means that there exists a ball of radius which is just a little bit more than the length of the edges that captures a big fraction of the vertices. This means that most of the distances collapse. Okay, is this definition clear? Is the most important slide we talked about. Okay. Okay, let me give a simple example. Hopefully this will help a little bit for the intuition. So let's prove that Xc for a real line, so this is one-dimensional space, for this parameter epsilon, epsilon is the conductance, is upper bounded by 1 over epsilon up to constants. Okay, so here's the proof. All right, so we have a graph, right? We have this embedding, right? So this is the function that maps vertices into reals. Okay, so now we can write the definition of lambda 2, the second largest eigenvalue of the adjacency matrix of the graph. If you write it in the correct form, this is what you'll get, right? That the average square distance for two random points, right? So this is a few minus a v for two random points, squared is upper bounded by 1 over 1 minus lambda 2 of the graph times the average distance of the average square distance of the edges. Okay, this is basically the definition of lambda 2. And now what I want to say is that either there must be a small ball that captures a high fraction of the points, and the radius of that ball will be at most 1 over epsilon, or there is a sparse cut in this graph. Okay, so we'll proceed from here. So first of all, notice that we'll use the fact that all the edges of the graph have distance at most r. So this means that the expected squared length of the edges is at most r squared, just because each of these is at most r. Okay? All right. So now, if it happens that there is no ball of radius roughly r by epsilon, which contains omega n vertices, this means that the average distance, this quantity, must be at least r by epsilon squared. Right? If this is not true, then there is a ball of radius, basically by Markov, there exists a ball of radius r by epsilon, which contains a constant fraction of the vertices. Okay, and now we have r squared by epsilon, r by epsilon squared here. We have something that involves lambda 2. We have r squared here. Just doing immediate calculation implies that 1 minus lambda 2, basically the spectral graph of a graph, must be smaller than epsilon squared by a constant factor. Now we can apply Chigre inequality. This means that there exists an epsilon sparse cut in this graph, and we've got basically our sparse cut.
What is F here?
F is the embedding. So you can think about F gives to every vertex gives a real number.
You're supposed to do this for all graphs, right?
Yes.
But, do you pick only regular graphs? That's okay.
Yeah, just because it's it's something that fits on 2 lines on slide. I mean, you can prove the same for non-regular graphs and so forth.
So where does Xi actually enter this picture?
Xi, this is Xi. What does it say? Either there exists a ball,
Oh, the
r times Xi, right? So this is here. So r times Xi, which says 1 over epsilon. Okay, any more questions here? Okay, and once we've proven this, we immediately get the same statement for Euclidean space as well. Just because Euclidean space is some of the, since L2 squared is additive over coordinates, we have squares here, so we get exactly the same upper bound on Xi for Euclidean space as well. Yes?
But Chigre is not tight, right? So, but this is still tight. Is like the Xi bound that you got, can you beat that? Because for Chigre, technically, it could be that you get epsilon instead. Right?
I think this bound is tight, but yes, right?
Well, just take a line graph and embed it into integers.
Yeah, but Chigre is actually tight for the line.
Yeah,
Chigre is tight for part.
Yeah, okay.
Okay, so this is this is for real line for Euclidean space, but this is not why we're doing this. The question is, okay, how does it work for other norms? Okay, so first of all, the cutting modulus is well behaved under embedding. So in particular, for example, if our metric space embeds into L2 with distortion, which is denoted as C2 of M, then it is immediate to prove that Xi, pretty much by combining with the previous slide, that this Xi is upper bounded by C2, basically the best distortion of an embedding into Euclidean space. But the point is that we can that Xi for many norms is much smaller than this bound, than the best distortion of embedding into Euclidean space. Okay, and as Sash already suggested, it's related to how well can we embed large expanders into our metric. Okay, so in particular, let me state some bounds for cutting modulus for norms. So the baseline, again, this is kind of by embedding. It's immediate to get that with Xi for any d-dimensional space is d-dimensional norm is upper bounded by root d by epsilon. But it turns out that for norms one can get a much better bound. One can get log d by epsilon squared, and this is a result of Asaf Noor from about a year ago. Okay, so this is a non-trivial theorem. This is a paper in itself. It's so, and one can get better bounds for special cases. In particular, for LP space, one can get order p by epsilon, static modulus. For p bigger than 2, this follows from work of Matushik, and for shorten p, one can also get something like order p by epsilon, and this follows from works by Matushik, Nauer, and Ricard.
I guess the main goal is not to improve the epsilon, but is it like?
Yeah, it is not improve the epsilon here. Yes, I mean, of course, now it's interesting to get the tight bound by epsilon, but for approximate nearest neighbor search. But in terms of Xi, I don't know if this bound is this dependence on epsilon is tight or not. Actually, is it?
We don't know. I think
we don't know. Yeah. But in terms of dependence on log D and P here, these bounds are tight for cutting modulus. Okay, so this was cutting modulus. So now let's show that basically if you get a good bound on cutting modulus, this implies a good nearest neighbor search algorithm. So this is the theorem, the more algorithmic theorem. The main contribution of the paper is to prove the following theorem that says that for any metric space, there exists a randomized approximate nearest neighbor search data structure, which obtains approximation upper bounded by Xi. For any epsilon, Xi as a function of that epsilon, up to constants, space will be n to 1 plus order epsilon times something which is polylogarithmic in the size of a metric space. And I should mention that for d-dimensional norm spaces, we can think about. You should replace log x with d here, as in this will be polynomial in dimension. And the query procedure inspects n to order epsilon times again polynomial in the dimension memory locations of a data structure. Okay, so this is the theorem. Okay, and the main message is that if a space does not contain large expanders, meaning that Xi is relatively small, then approximate nearest neighbor search is possible, at least for cell probe algorithms. All right, so let me tell you how to obtain this theorem, and let me tell you about this core partitioning procedure. So think about the metric space. Defined on a space X. It's much simpler for us to think of X as being a finite set, and you can think about this as being the size of the space as being exponential in dimension. For norms, you start, of course, with a set of which it has infinite size, but you can discretize and do visual reduction so that you really have to consider on a finite space X. So we need the following partitioning procedure to build a collection F. So F are sets on X, such that for any endpoint data set called P, we have the following. Either there exists a ball of radius. Okay, so for this data set P, either there exists a ball of radius r times Xi, which contains many points, omega n points. Okay. So this means that within this ball of radius, all the points are at the distance roughly r times Xi, so kind of close to each other. Is Xi small? Okay, so it looks something like this. Or if this doesn't hold, okay, so you need to connect to this collection. There exists a distribution D of cuts that partition the point set roughly evenly. Okay, so this means that so something like this. So somehow partitions into, let's say, purple and green subsets, which are roughly each of them is of size omega n, such that the following holds. For any 2 points, x1, x2, which are close, so a distance at most r, the probability that a cut chosen randomly from this distribution over nearly even cuts will separate x1 and x2 is upper bounded by epsilon. Okay, so this again says there exists a collection. Okay, so kind of ground set of sets, such that for any data set point, unless there exists a ball that contains many points, again, the point set is relatively nearby to each other, there exists a distribution over near balanced cuts over P, such that any close point is separated, when we choose a cut randomly from this distribution D, this probability is upper bounded by epsilon.
What's the role of F?
The distribution is defined on F. Distribution D is on the cuts from F. As in, this is the set of allowed cuts. Okay, and the point being that the size, the number of allowed cuts is very small. In particular, log of F is order of D cubed.
You mean the cuts in F, they're only basically like taken from, so the other way. D is like only like giving weights to the cuts that are already given in F.
Yes, yes. So F is the set of allowed cuts, okay, and distribution D is just saying how many probabilities, yeah. So in particular, log of F is polynomial in dimension, and D is over D by epsilon sets from F. In particular, this means the distribution D can be described with polynomial in dimension size. So description complexity of its distribution D is small.
So is this where your cell probe versus algorithm problem?
Yes, yes, yeah, we'll get there. Yeah. Okay. So this is the core partitioning that we are getting, and it turns out that this is enough for approximate nearest neighbor search using more relatively standard, now standard techniques. Okay, and just to say something kind of about connection between cutting modulus and obtaining this copartitioning, the cutting modulus says the following, that we can find, so cutting modulus being small, this means that we can find an epsilon sparse cut in a graph with short edges and where all the vertices are separated by xi. So this means that there is no small ball. This means that vertices separated. So for any graph that satisfies this property must have an epsilon sparse cut. So this is something that we're given kind of from the property of a metric, right? This is what it means for cutting modulus to be small. What we want to get, this is the partitioning that is sufficient for nearest neighbor search, is to say we want a random partition that is good for every pair of close points with goodish probability with epsilon, and the description complexity of this random partition is relatively small. Okay, yeah, and I'm about to finish. And how do we go from here to here? This is essentially minimax. Very long enough at it. So it is duality in the spirit of minimax theorem. And to go from left to right, we apply basically multiplicative weights update method. It's actually two MWU algorithms nested in each other. And we need to use multiplicative weights update specifically to get this small description complexity. Okay, so in the interest of time, let me just quickly kind of give advertisement for the next talk. So the cuts, the algorithmic aspect. So what is the issue? Why do we get the cell probe algorithm? Well, the question is, how do we check on which side of the cut we are? Right. So the cutting modulus guarantees us that there exists, unless the points are, clustered, there must be a cut in our graph that we consider. And how do we check on which side of the cut we are? Right? So we have a bunch of points. We are guaranteed that there exists a small cutting modulus, means that there exists some cut that partitions, the points that corresponds to the partition of the graph. But the issue is that this cut comes from second eigenvector. Okay, right? This comes from applying Chigurh's inequality, and there is no a priori structure. As in, these are some crazy graphs on the entire metric space, and there is no a priori structure. So this means that the partition that we get on the points may be arbitrary. Okay. So the cuts can have very complex boundary, and there is no clear algorithmic tool to compute on which side of the cut you are. So what we really need is that if graph is embedded into metric or norm space and has small xi, then there is actually a geometrically algorithmically nice sparse cut. And an example of a nice sparse cut is something that looks like this. In particular, it's a coordinate cut. Okay, and for LP, one can always find a coordinate cut, in fact, that obtains this xi upper bounded by order p. Okay, so this will, same for short MP. So this is something that Ilya will mention a little bit in the next talk, and I'll conclude here. So again, the main point or the main thing that I wanted to say about here is cutting modulus, which is generic recipe from going from xi. By the way, this cutting modulus arose from the theory of nonlinear spectral gaps that Asaf Naor was developing for a few years now. And so this leads to approximate nearest neighbor data structure algorithms. And the main questions kind of that remain is, first of all, to get time-efficient data structure for any norm achieving log D approximation, so going from cell probe to an actual algorithm. So in the next talk, you'll see, a step towards there, obtaining a bound which is somewhere between polylogarithmic and polynomial. Another question that we don't know how to approach at the moment is to obtain polynomial preprocessing time. So all our current algorithms have exponential preprocessing time, even for spaces like LP. And another question is to obtain cutting modulus, to obtain better bounds on cutting modulus for concrete spacing, like eddy distance or Wasserstein metric, Riemannian manifolds, or other nice important metrics that one cares about.
The next talk's in just a few minutes. If there's a quick question, you can ask Alex. Otherwise, we'll break this use the restroom or something. All right, we can probably ask more questions during the next talks.